You're referring to question is about example 2, right? And which line did you state? Okay, the where I went from polar to rectangular. Okay. So from 20 angle minus 45, I went to 14.14. Yep. So yeah. So yeah, minus 45 means if this is the real axis, minus is in this direction, 45 would be, and this is the imaginary axis. So minus 45 would be somewhere here. This is minus 45. Actually, let me change the screen. Sorry. So minus 45 means I'm going in a clockwise direction. The length of the vector is 20. And when I project this on the real axis and the imaginary axis, well, 20 is the hypotenuse. And because it's minus 45, both the sides would be exactly the same, A and A. And so the conversion would be 20 is equal to square root of A square plus A square. And that's how you get 14.14. But this is, again, the graphical illustration is for students' understanding. This is not something that you have to do when you're solving a problem. This is done on a calculator. Okay, this conversion is done on a calculator. If we, as an engineer, if we sit there and try to do this manually, I mean, if it's like a critical mission, obviously you want to check and double check and triple check, multiple times, obviously. But when you're trying to solve a problem like this, you use the tools that are at your disposal. Okay, polar to rectangular and rectangular to polar conversion is something that all calculators can do. Also, there are lots of online websites where you can do this. Okay, so when I'm in a rush and I don't have my calculator with me, I'll just open up that website that I've bookmarked and I just enter the coordinates. It'll just give me an output. And so this is something that we use tools to speed up the process. Again, this is for explanation purposes. The graphical illustration that I've done here is to explain to students. This is not something that we would typically do when we're trying to solve problems. Does that make sense to everyone? Okay. All right, let's move on to examples 3 and 4, and then we'll get to 5 after that. So example 3 is about an inductor. Example 4 is about a capacitor. Both of them would be exactly, well, not exactly the same. They would be very similar because we are applying Ohm's law. But let's see how we're going to represent the impedances using complex numbers. So what are we given? We are given the value of an inductor and the value of the capacitor, meaning the component values are given to us, and VL of t, meaning the voltage across the inductor is given to us, and VC of t, voltage across the capacitor, is given to us. So let's take example 3 first. Okay. Voltage for an inductor is given, and we are asked to find the current. Okay, this is incorrect, and this is incorrect. We don't need that because that's already given. So voltage for inductor is given, and we are asked to find the current. Think back to chapter 3. If you wish to find the current for an inductor, what do we do? Just as a refresher, let me write out the inductor equation. V or VL is L times the derivative of the inductor current. So if you wish to find the inductor current, you must integrate the voltage. So integrate the voltage, VL, and then obviously divided by the inductor. we'd have to perform this expression. Obviously, we can do this, right? We can integrate this expression. We can perform the math, but an even easier way exists if we represent the inductor with its impedance, then we can apply Ohm's law. We can apply Ohm's law and we can directly write VL is IL times ZL. And I'm using a slightly different variation of the uppercase letters just to indicate they're all complex numbers. Okay. So again, inductor component value is given to us. Voltage in the time domain is given to us, VL of t. We are asked to find the inductor current. So we can use the standard expressions, perform the derivation, perform the integration, and find it that way. Or we use complex numbers and we simply apply Ohm's law. Get the answer in a couple of steps. Okay. So as I was said at the beginning, we use complex numbers to make the math less complex. ZL is J omega L. Omega is 2 pi f, so it's J 2 pi f L. J multiplied by 2 multiplied by pi multiplied by f multiplied by L. That's what it means, J 2 pi f L. Okay, all quantities are multiplied in this case. In polar coordinates, ZL can be written as omega L with an angle of plus 90. So again, 2 pi FL, magnitude of 2 pi FL with an angle of plus 90. And I will explain the significance of plus 90 and minus 90 after we get done with this example. Okay, these are the standard equations. J omega L in rectangular coordinates and omega L with an angle of 90 in polar coordinates. So when we wish to find the impedance, we need omega values, right? Omega is 2 pi f, meaning I need the frequency. So as a first step, you would take your source and compare it to the standard expression and extract all information from there. So we compare it to the standard expression, which is V of t is Vm cos of omega t plus theta. From there, I can write Vm is 100 volts. Omega is 200 radians per second. And theta is 0 degrees. Okay. Again, when we wish to find impedance, we need omega. So to find omega, we compare the given voltage source or the current source with a standard expression and extract three quantities or extract information about three quantities: the magnitude, the frequency, and the phase. So magnitude here is 100 volts, frequency omega is 200 radians per second, and the phase is 0. Also, keep in mind, if the expression is in sine and not cosine, you must convert it into cosine first before you write down the phase angle. If this expression was, now this example within an example, if this expression was 100 sine 200t, I would convert it into cosine first. So it would become cos of 200t minus 90 degrees. And then I would compare it. So my Vm would then be 100, omega would be 200, and my theta would be minus 90. Okay. So always keep those concepts in mind. All right, let's proceed. So we have omega, we have our phase angle, we have the magnitude. I'm directly going to write out the phasor for the inductor voltage VL, which is 100 with the angle of 0. Then I want to find the current I. I would be, from Ohm's law, I would be given by V over Z, voltage divided by the impedance, Ohm's law. So I need to perform a division. If I'm performing a division, I would want all of my quantities in polar coordinates. So when I find ZL, I'm going to use the expression omega L with the angle of 90. Find it in polar coordinates. Omega is 200. Inductor value is 0.25 Henry, given in the problem statement. It's 200 times 0.25 with an angle of with the angle of 90, gives me an impedance of 50 with an angle of 90 ohms. The units do not change. 50 with an angle of 90 degrees. And once you have that, you can directly write out IL. Phasor for IL would be VL divided by ZL. VL is 100 with an angle of 0. ZL is 50, 90 degrees. This becomes a vector with a length of 2 and a phase angle of minus 90 amps. If the problem statement asks you to find the phasor, you can stop right here. Or if it asks you for the answer as a function of time, meaning IL of t or V of t, then you must perform the inverse phasor transform and display your final answer in the time domain. So IL of t would be 2 cos of 200t minus 90 degrees amps. Let's take a pause. Let me know if you have any questions. Any questions? Do the steps make sense? Okay, well, let's go ahead and solve example 4, and then we'll get to 5. So I'll go through example 4 with, let's see. If the noise bothers anyone, I can close the doors. You guys okay? Right. All right, example 4 is very similar, except the equation would be a little bit different because it's a capacitor. Capacitor value is given, voltage is given, both of them are in the time domain. If we wish to find capacitor current, it is given by the product of C and the derivative of the voltage, dVc over dt. Perform a derivation of this expression, multiply it with the capacitance, and you obtain your answer. Of course, it's a simplistic case, but let's see how we do with a complex number. So first things first, compare Vc of t with the standard expression, and I can write magnitude of the voltage is 100 volts. Omega is 200 radians per second, and phase angle theta is 0 degrees. The only difference this time is that the impedance of a capacitor is given by 1 over j omega c, or in omega is 2 pi f, so 1 over j 2 pi fc. In polar coordinates, it would be 1 over minus j would convert to an angle of minus 90. Minus 90. These are the standard equations for the impedances of a capacitor and an inductor. Okay, so you can write ZC as 1 over 200 times 100 microfarads. Omega is given as 200 radians per second, so 200 times capacitance value, which is 100 microfarads, 100 times 10 raised to minus 6, and that's the denominator, and then angle of minus 90. This gives me a value of 50, the angle of minus 90 ohms. Okay, ohms. Always keep that in mind. Even if the answer includes degrees, the overarching units for that quantity would be ohms. And then IC would be the phasor for VC divided by the complex impedance is ZC. Phasor for VC would be 100, magnitude of 100 divided by magnitude of the impedance. The phase angle is 0 minus of minus 90. Okay, minus of minus 90. Let me write out the steps so that there's no confusion. VC is the phasor form. Phasor form would be 100 with an angle of 0 divided by 50 with an angle of minus 90. That would become 100 divided by 50 and 0 minus of minus 90. And therefore IC would be magnitude of 2 with an angle of plus 90 amps. And IC of t would be 2 cos of 200t plus 90 degrees amps. That would be your final answer. Let me know if you have any questions. Let's take a pause, longer pause this time while you write it down. Let me know. Do the steps make sense? Any questions? So there are two things I want students to pay attention, right? There is a circuit analysis portion, and then there is the math portion. The circuit analysis portion has not changed. That is still the same as what we, as what we learned in chapters 1 and 2. Okay, this is a simple application of Ohm's law. The math has changed. Okay, so this entire chapter, the circuit analysis techniques remain the same, but the math is different. And it would be to your advantage to practice this as much as possible, because again, this math is not unique to electrical engineering. As an engineer, you would have encountered this in your own fields, or you probably will encounter it at some point. Okay, so only the math is new with regards to the material. The circuit analysis techniques are still the same. Are we ready to combine it all together and go to example 5? Okay. Oh, before we do that, I do want to take this moment and talk about where the plus and minus 90 comes from. Okay. Actually, instead of this place, let's go and talk about it here. Impedance for a capacitor and an inductor. Okay. And why it is plus 90 for a inductor and minus 90 for a capacitor. So from Ohm's law, we know V equals IZ, product of the current and the impedance. V equals IZ. So what is Z? Z is voltage divided by current. Impedance is the voltage divided by the current for that component. For that component. If we perform this math, we can write magnitude of voltage divided by magnitude of current, and theta V minus theta I, meaning the phase of the voltage minus the phase of the current. We can also break it down like this. Magnitude of the impedance is magnitude of the voltage divided by the magnitude of the current, and theta Z, phase of the impedance, is the phase angle of the voltage minus the phase angle of the current. Okay. Theta I. Make sense? You guys with me so far? Okay, so now that we have established this, right, impedance is voltage divided by current. In mathematical terms, if you're using complex numbers, then the impedance has a magnitude and it has a phase angle. And because it is a division, the operation of voltage divided by current becomes the magnitude of the voltage divided by the magnitude of current, and the phase angles are subtracted. The phase angle of the voltage minus the phase angle of the current. Now, here's the thing. In an inductor, if we have a voltage, and let's say this is 90 degrees, for an inductor and a capacitor, there is a phase difference. Can't control it enough. Approximately. Let's say this is inductor current IL, and this is inductor voltage VL. The magnitudes don't matter. The height would be different, right? I mean, you could apply 10 volts to an inductor and the current could be like 1 milliamp or 5.7 milliamps. So if you try to plot both the same graph, it wouldn't work. The frequencies, of course, remain the same. The frequencies are not affected by the components. The only thing that is affected, the only two things that are affected is the magnitude or the amplitude, and then also the phase. Because energy transfer is taking place, there is a phase difference between the voltage and current. Okay, they arrive at separate points in time. Okay, so without going too deep into the technical know-how, there is a phase difference between the two. The voltage for an inductor is always ahead of the current by 90 degrees. And this is indicated right here. If it's ahead, if it's on the left, remember again from earlier in this chapter, all values to the left, meaning it's in the past, it's already gone by, it's already ahead. So if a waveform is to the left, it means it is ahead, meaning it has a positive phase difference. Okay, so this is ahead. Let me write, since I'm using color notations, the voltage is ahead of the current. In technical terms, ahead means it is leading. Okay. In technical terms, ahead means it is leading. So for an inductor, voltage is ahead of the current, always by 90 degrees. Okay, always ahead of the current by 90 degrees. VL always leads IL by 90 degrees. This is specific to one single inductor. Okay, you are not comparing the voltage of one inductor to the current of a different one. Then that phase could be anything. If you're talking about one single specific component, then the voltage of that inductor is always ahead of its current by 90 degrees. Always. Again, that is due to laws of nature, laws of physics. It's an inviolable law. Okay, the environmental conditions, temperature, everything being the same. Let's say we're talking about room temperature device. Current is always 90 degrees behind. The other way of stating this is that current is behind voltage. And the technical term for that is lags. Actually, since I'm using leading, let me use lagging. So in the same terms, I can write voltage is leading the current or current is lagging the voltage. Depends on your perspective. If two people are walking down the street, you could say person A is ahead of person B, or you could say person B is behind person A. So it means the same thing in this case. Voltage is ahead of the current by 90 degrees, or current is behind the voltage always by 90 degrees. So there is a phase difference between the voltage and the current of plus 90. Okay. So if you do ZL, when you perform ZL, it would be theta V minus theta I, or theta VL minus theta IL, and that would turn out to be plus 90 always, because the voltage for an inductor is always ahead of its current by 90 degrees. So it'll always be a phase difference of plus 90. For a capacitor, it's the exact opposite. For a capacitor, I'm going to draw this out here. This number a little faster. Capacitor current IC is always ahead of its voltage, VC. So you could write voltage is ahead, voltage is behind the current. Or current is ahead of the voltage. Current is ahead of the voltage. And again, in both cases, the difference is 90 degrees. So ZL was plus 90, ZC would become theta VC minus theta IC. That equation does not change, right? Impedance is always voltage minus the current. The phase angle of an impedance is always the phase of the voltage minus the phase of the current. But because the voltage is behind the current, meaning voltage for a capacitor lags the current, there's always a difference of minus 90 degrees. This is a constant. This is inviolable. That does not change. So a capacitor impedance is always minus 90 degrees. An inductor impedance is always positive plus 90. That's where it comes from. This is simply the explanation behind the equation. Okay. When you're applying the equation, do not get too bogged down into how it's plus or minus 90. It's a standard expression. You simply take the expression and write out your equation. That's where this comes from. There's a mnemonic that we use. Eli the Iceman. So named after Eli Manning, because he's got ice in his veins. Anyone know who Eli Manning is? Not really. This predates Eli Manning. It's from a long time ago. We know that L and C stands for inductor and capacitor. We know that I stands for current. What does E stand for? Electromotive force or voltage. So for an inductor, the voltage always comes before the current. For a capacitor, the current always comes before the voltage. That's how this mnemonic works. Eli the Iceman. For an inductor, voltage is ahead of the current. For a capacitor, the current is ahead of the voltage or comes before the voltage. And in both cases, it is by 90 degrees. 90 degrees. If you wish, you can switch out the arrow to point the other way so that it's plus 90 and minus 90. Okay. Make sense? All right. And again, this is just the explanation for the concept. There are many other details, of course, we can go through. There's physics that we can understand of why this happens. And again, this is not a physics class. This is a circuit analysis class. So let's move on to example number 5. Okay, we got 20 minutes and that's plenty of time to go through this. So we have a circuit comprising of resistor, inductor, and capacitor. One voltage source, which is given to us, and we are asked to find the total current that is flowing through the circuit. We're asked to find the resistor voltage, capacitor voltage, and the inductor voltage. So first thing that we would do when we have a circuit like this is I would tell students to draw the equivalent impedance diagram. And what I mean by an equivalent impedance diagram is you replace every single component with its impedance and you redraw the circuit. Okay. I'll make this large. So resistor is replaced with its impedance. Capacitor and inductor also replaced with its impedances. Resistor, of course, remains exactly the same. Doesn't change. R is still 100 ohms. And then, of course, the source is replaced with its phasor. Polarity still remain the same. Phasor of Vs. Current I is also replaced with its phasor. And phasor for current I, simply Is, or just I. The series circuit has the same current I flowing through all components. Okay, so first step, draw the equivalent impedance diagram. What this does is it allows us to visualize the circuit as it is from chapters 1 and 2. Okay, from chapters 1 and 2. So what techniques would you use if this was a DC circuit from chapters 1 and 2? What technique would come to mind first? Any guesses? Mesh, node voltage, series parallel analysis. But it's a single loop. So if you apply mesh current analysis, it would be the same as applying series parallel, finding like REQ. In this case, you would find ZEQ. So you'd find ZEQ as seen from the perspective of the source, apply Ohm's law, and then find the voltages. So the circuit analysis, again, is straightforward. It's the same thing that we learned in chapters 1 and 2, but the math is different. So we'll talk about the math, okay? So I'll quickly outline the steps. We'd find ZEQ. So determine ZEQ. Apply Ohm's law. Determine total current I, and then apply Ohm's law again. And determine the voltages. What is happening here? Sorry, my pen and mouse cursor were fighting. Determine the voltages. So again, the steps have not changed. Circuit analysis is still the same. It's only the math that is different. So let's find ZEQ. What would be ZEQ? ZEQ would simply be, because it's a series circuit, ZEQ would be R plus ZL plus ZC. R plus ZL plus ZC. We'll do two more things. Vm, omega, and phase angle theta. So I'll write down Vm is 100 volts. Omega is 500 radians per second. And theta, phase angle, is 30 degrees. I'll write out the phasor for Vs, magnitude of 100 volts, phase angle of 30 degrees, unit of volts. Okay, unit of volts. Let's see, how much time do we have left? 15 minutes, okay. So let's write out ZL and then ZC and then find our ZEQ. Now, typically when I solve these problems from habit of years and decades, what I do is I try to find out complex quantities in both polar coordinates and rectangular coordinates at the beginning of my analysis, because I never know how the analysis is going to go. And so instead of trying to find it at a later point, I have them both at hand. And so it's convenient when I perform that analysis calculations. So I'll find out ZL in both rectangular and polar coordinates. In ZL in rectangular coordinates would be J omega L. So it's J times 500 times the inductor value, which is, let's see, what is the inductor value? 0.3 Henry. So 0.3, and this would be J 150 ohms. J 150 ohms. And of course, writing out the polar coordinates would be straightforward too. It's simply the product of omega L with the angle of plus 90. And so it's simply 500 times 0.3 with the angle of plus 90. So it becomes 150 with the angle of plus 90 ohms. If there is no real component and it's a positive value, means positive imaginary number plus J something, that means it's always pointing straight up, right? It's 0 plus Jx. Real quantity is 0, and it's simply pointing straight up, plus 90. Similarly, ZC is 1 over j omega c. 1 over j omega c is j times 500 times my capacitor value, which is 40 microfarads, and 1 over. And this gives me minus j 50 ohms. Minus j 50 ohms. And at the same time, in polar coordinates, ZC is 1 over omega c with the angle of minus 90. And so it's 500 into 40 into 10 microfarads. 40 microfarads. And this would be 50. Angle of minus 90 ohms. Minus 90 ohms. So I want to find ZEQ. ZEQ means I need to add up R plus ZC plus ZL. It's a series circuit. If it was parallel, you would do the parallel equation. Have ZL and have ZC, and then you add it up. Sidebar, 1 over J or 1 over I, reciprocal of the imaginary number is minus J. You could write this out as 1 over J times J over J. This becomes J over J square, which is J divided by minus 1, hence minus J. Reciprocal of the imaginary number is the negative imaginary number. Okay. So ZEQ is R plus ZL plus ZC. This would be 50. No, R is 100, sorry. Resistor is 100 ohms plus J 150 ohms minus J 50 from the capacitor gives me a ZEQ value of 100 plus J 100 ohms. And at the same time, I will also write out the value in polar coordinates. 141.14 or 141.4 with an angle of 45 degrees ohms. So far, so good. Any questions? Now, if this was a series circuit and I asked you to find the voltage, what other technique comes to mind? Series circuit, applying a voltage, what happens to voltage? Voltage gets divided across all the resistors. The same thing happens here. You apply a voltage to a series connection of impedances, a fraction of that voltage appears across each impedance. So if we didn't need to find the current, we could apply voltage division and find the answers directly. What I'm going to do is, well, I won't skip over that step because I want to show you how to find the current and then find the voltages. But I will write out the equations so you can practice. Okay. So VR would be Vs times R divided by ZEQ. VL would be Vs times ZL divided by ZEQ. And VC would be VS times ZC divided by ZEQ. So once I go through and solve this, you would have the answers at your disposal. You would have VR, VL, and VC. I would suggest or strongly recommend that you practice using these equations and see if you can obtain the exact same answer. Okay. So let's go ahead and do this. I have about 7 minutes left, so I'll go over the steps, but the calculations will jump a little quickly. Applying Ohm's law, I is Vs over Zeq. Vs is 100. So magnitude of 100 divided by 141.4, magnitude of the impedance. Phase angles are subtracted, so 30 degrees minus 45 degrees. And my current turns out to be 0.707 with an angle of minus 15. The time domain expression I of t would be equal to 0.707 cos of 500t minus 15 degrees amps. Okay. So once you have the current, you can find the voltage again by applying Ohm's law. VR would be I times R. This would be rather straightforward because I is 0.707. There's no other phase angle. So it'd be 0.707 times 100. And then the phase angle would be minus 15 plus 0. A resistance, remember, behaves the same for AC and DC. It does not change the phase at all. It does not affect the phase. So the phase angle for a resistor is always 0. Okay, phase angle for a resistor is always 0. So when you try to find the voltage and current for a resistor, they would always have the exact same phase angle. So if the current passing through that resistor has an angle of minus 15, the voltage for that resistor will always also have an angle. Sorry, the voltage also will have an angle of minus 15. So VR would be 70.7 with an angle of minus 15 volts. And VR of t, time domain expression, would be 70.7 cos of 500t minus 15 degrees. VL similarly would be I times ZL. So 0.707 times the magnitude of ZL, which is 150, phase angle minus 15 plus 90 degrees. That gives me an answer of VL as 106.08, or yeah, let's see. 150 times 0.707, 100, I think it's 0.08 with an angle of plus 75 degrees and volts. Time domain expression, lowercase typically means the time domain expression. So VL of t is 106.08 with an angle of cos of 500t plus 75 degrees volts. VC, capacitor voltage, is the current times ZC. So 0.707 times 50. Phase angle would be minus 15 plus minus 90. Remember, it's a multiplication, but you have to keep the signs constant. If you ignore the signs, your answer would be minus 15 plus 90, which would be incorrect. So cos of 500t minus 105 degrees. I skipped 35.35 with an angle of minus 105 volts. And therefore VC of t is equal to 35.35 cos of 500t minus 105 degrees. Those are your three voltages. So let's take a longer pause while you write it all down. Let me know if you have any questions. Any questions? Any questions at all? We are almost at the end. I just want to draw out the phasor diagram. So the phasor diagram for this would simply be plotting the vectors, okay? So you plot the vectors on the real and imaginary axes. Let's draw this out. So this is the real. Let's draw out VS first. VS has an angle of, excuse me, has an angle of plus 30. So let's see, 1/3 of this about here. That's still like 45, not 30. So let's say this is vector for VS, the source voltage. The length of this is 100. Obviously, this is not to scale. Okay, not to scale. Current I, I'll draw that out later. What I'm going to do is I'm going to draw out the voltage for the resistor, which is at minus 15. So again, this is not quite indicative of minus 15. Perhaps here, maybe. I don't know. So this would be VR, and it's minus 15. This angle is 30 degrees. And VR has a length of, let's see, what does VR have a length of? 70.7 volts. So this is 70.7 volts. Then is the current. Now, obviously, this is not to scale because the current is only 0.707 on the same axis. This is the current, and current has a length of 0.707 amps. So again, obviously not to scale. Does that make sense? Phasors are nothing but vectors. So if you wish to draw a phasor diagram, you simply take the angle of the vector, mark the position on the diagram, and draw out a vector, mark the length as the magnitude of the vector. And that's it. It doesn't have to be to scale. Now let's draw VL. VL should be 90 degrees ahead of the current. So somewhere about here. This is VL. It's plus 90 with respect to the current, but with respect to the real axis, it is plus 75. That's where we plot it, plus 75. But the current is the same for all, so plus 90. And capacitor would be right here, because capacitor is minus 105. With respect to the current, it's minus 90. So this is VC. And VC has a length of 35.35 volts. And VL has a length of 106.08 volts. I'm sorry, I've gone over time, so if you need to leave, feel free to leave. I'll just finish this, and you can watch the recording if you have to leave. But that's the phasor diagram, okay? And again, as a reminder, going clockwise, positive angles go clockwise, counterclockwise, and negative angles go clockwise. Okay. So there's a lot of information here. Feel free to ask any questions that you may have. I'm going to end or stop the recording here, and I'm happy to answer questions